Welcome back. Let's get stuck into some Boolean logic. So we need Boolean logic to help us address this question. But before we do so, we need to understand what Boolean logic is. So Boolean logic is a type of algebra in which results are calculated as either true or false. So it's known as truth values or truth variables. So we could have different conditions, and we see whether what happens if both of them are true, if one of them is true, if the other is true, if there's none of them are true. What's the outcome of these sort of combinations? And these outcomes vary as a function of the operators that are used. So the Boolean operators are and, or not. Okay, so let's start with the and operation. So this is called a truth table. It allows us to visualize what happens in each of these scenarios. So say we have a scenario where we have a big data set and we want to only select participants who are from Australia and are over 50 years of age. Yeah. So what this means is we want to select only people who fit the criteria of both. We want them to be, say A is Australian and B is over 50 years of age. So in this case, we'd use an AND operation. And if both are true, the outcome will be true. So what this means is in Jamovi, it'll go row by row and it'll see, well, does it tick the box for Australia? Does it tick the box for age being greater than 50? Okay, let's include that. And it'll put a tick next to it. Now, if you've specified an AND operator and Jamovi's going line by line and it says in the second row here, it says, oh, okay, it says it's Australian, that person or participant is Australian, but less than 50 years of age, the outcome will be false. And so Jamovi will put an X there because we've specified an AND operation to occur. Similarly, vice versa, if the Jamovi goes through the row and says, person's not Australian, but they are greater than 50 years of age, because we've specified an AND operation, we want both statements to be true, the outcome will be false in that scenario. And the final one is if both are false, if someone's from a different country and less than 50, the outcome will be false. So Jamovi uses these operators to select rows in your data set. So if you specified an AND situation just like that, that's a way it'll be used. And we'll revisit this concept again in a second, but it's useful to let it marinate with the AND operations, and we'll come back to it. The next one's the OR operator. So imagine a situation where I say I want to select people in a data set who are Australians or greater than 50 years of age. So Jamovi will go through each of the rows and it says, well, if both are satisfied, if it's Australian or and greater than 50 years of age and they're both satisfied, we say that's true. So we'll give a tick next to that row. Because it's an OR operator, though, it only requires one of them to be true for the outcome to be true. So if it goes through the rows and sees that the Australian category is met, then the outcome will be true. If it sees the greater than 50 category is met, even if the country isn't, the outcome will be true with the OR operator specified. And then if neither are true, if it's not the right country or if it's not greater than 50, then the outcome will be false. So this can be a powerful tool if you're specifying, if you want to select specific participants, if you want them to meet both conditions, such as if they're Australian and greater than 50, or if you just want them to meet one of the conditions. And you can see the combinations in which Jamovi will process it and apply it to your data set. The final operator isn't just a not operator, so it's the opposite. So say if we wanted the participants who are not Australian. So if that's the case, then it goes through each cell and it sees those that are Australian, it'll be false. So if it's true for Australian, it'll be the not operator, it'll be false. And then for those who are not Australian, it'll be true. So it'll select just the ones that are not Australian, if that's what we're after. So that's Boolean logic. Its uses are in data analysis and what we're doing right now in terms of filtering data sets, selecting specific populations or specific characteristics. It can actually also be used with searching the literature for key terms. So if you go onto something like PubMed, Google Scholar, PsycInfo, all of these databases behind it have a machine in which it allows it to search the wide data that it has available and select the best things for you. in part, you can manipulate your search to make sure that you're getting the most accurate returned results based on the search. And this includes Boolean operators. So say I was interested in the association between using Jamovi and happiness. Say if that's the case, I want papers that look at both Jamovi and happiness. I don't want papers that look at Jamovi and statistical methods or Jamovi compared to other statistical programs. I just want papers that looked at Jamovi and happiness. To do this, I would go into any of these databases, so Google Scholar, for example, and I'd type in Jamovi and happiness, and it would return results if both of those criteria were met. But any of the others ones, that it would be further down on the list. So you can use this very strategically when searching the literature. And it's also important for developing critical thought. It allows you to have the stages of understanding how to frame or think about scenarios and outcomes based on what's being prescribed. So it's sort of the foundations of logical thinking facilitates critical thought the more you use it. So those are some examples of ways in which you can use Boolean logic. So let's go back to our question and apply this Boolean logic. So we want to see, how do the trends in life expectancy for Australians compare with those living in Ireland? So we need Boolean logic. We want to have the ticks next to the country that says Australia and also the countries that have Ireland in it. Now, if we use an AND operator for this, remember both have to be true. None of these countries can be both Australia and Ireland. It's impossible, right? It's reflecting the countries itself. But if we use an OR operator, if either one of them is true, the outcome will be true. So we can give this a go and show you the OR operation in action. So we just do country equals Australia, and we say OR country equals Ireland. We go enter. And now you see we have two lines here. We have two sort of trends that are here. And if we scroll all the way down, I wish I picked a country that was started with an A. But if we go all the way down, HI, and here we go. We can see Ireland. And you see how Ireland is now ticked. So because we've used the OR operation, Jamovi's gone through each line and said, well, if it is either Australia or Ireland, I'll select that and plot the resulting information. So let's do another question. How do the trends in life expectancy for Australians compare with those living in Ireland and Brazil? So have a go at that, see if you can do it, using the Boolean logic that we have just discussed. So if you want to do it with me, the way to do it is we just add, again, OR country, another OR operation, equal Brazil. Enter. Now we have three trends. And if we go all the way back up to Brazil, we can see it should now be ticked. Where are we? A, B. Brazil. There we go. So Brazil is now ticked, right? And so now you can use this quite powerful tool of OR operations, where if any of the categories are true, then the outcome will be true, and Jamovi will plot it for you. So I'd encourage you to ask yourself other Boolean logical questions. See what you can do to try to select parts of this data set. I've proposed some Boolean logical questions here that we can work through, but you can play around and see what you can work through and even modify scatter plots or get descriptives, all sorts of information. So let's work through all three examples using the OR and a NOT operation. So let's do OR. Let's just do life expectancy. We just want to filter life expectancy, which is greater than 50, or year is equal to 1952. So this will give me all the rows in which life expectancy is greater than 50, or year is equal to 1952. So this row here will be highlighted because it meets the criteria of 1952, and so will this one here, where it says 1952 there. So we can press enter and you can see it magically hit up. And because we're expecting life expectancy as well to be greater than 50, you can see that that will also be met here. So again, you can play around. You can see here that the life expectancy is not greater than 50, but the year is 1952. So that's why this one is ticked. If we change this operator to an and, which means both conditions require to be true, we can see that this Botswana in 1952 will no longer be highlighted. What happened here? In the AND operation, it has to be lowercase and. AND operation, we can see now, Botswana 1952 is no longer highlighted. So let's do country is equal to Australia or year is 2002. So let's do country equal to Australia or year equal to 2002. So it'll give me any of the options where the year is 2002, so all of the 2002 countries are selected. And also, if I go to Australia, all of it is selected because it all meets the criteria of Australia. Let's do the AND operators now. So we did one just then, just played around with, but let's do AND operators where both conditions must be met to be true. So let's do population is greater than 5 million. I think that is 6 years. 1, 2, 3, 4, 5, 6. And year is equal to 1952. So again, we can see the population where it's either greater than 5 million or the year is equal to 1952. Right? And that's what we see there. And year is equal to, so it has to be both 1952 and the year is equal to populations greater than 5 million. So here's an example in Albania, 1952, it's not highlighted because it is 1952, but the population's not greater than 5 million. And let's do another one where population is greater than 5 million and life expectancy is greater than 80. Life expectancy is greater than 80. And we can see there's not that many countries, but there's a few. Australia is up there, so that's good to know. And recent as well, 2007, 2002. So life expectancy is greater than 80. Population is greater than 5 million. Let's implement some not operators. So this was, again, it gives you the opposite of what you want. So I don't want any rows selected where the year is equal to 1992. So you do not equal to 1992. And this will gray out any of the cells where the data is equal to 1992. Right? And again, we can do same thing for country. So say I want the country, but I don't want any of the any Irish rows. Any rows where the country equals to Irish is true. So I'll go Ireland. And so all the data will be selected except if we scroll all the way down, E, F, G, H, I. Ireland is not highlighted out. So it's not reflected in the graphs or descriptives as you're working through. Again, with all these filters, you can just turn the activity on and off of them if you want to just see what it is with and without the results. So this can be a really, really powerful way to analyze your data, subset your data for specific conditions and see what happens. Particularly if you're doing outlier analyses and you've created perhaps, say, a column where the data set or data row is an outlier or not, or say Cook's distance is large, you can just give it a true false value, use these Boolean operators to select that, conduct the analyses, and then just do it with and without the participants who have the outlier as true or multivariate outlier as false, and then you can see what happens if your results change. So it's a very, very powerful tool for many, many reasons. So the next question we'll do is, what is the correlation between GDP per capita and life expectancy? So now we're going into correlations. So let's do this. So to do this, we go to Analyses, Exploration. We do correlation. So GDP per capita and life expectancy. So we go Exploration, Regression, correlation. We want to do a correlation matrix we can do. And then we do GDP per capita and life expectancy. Excellent. So we can see the correlation between GDP per capita and life expectancy is 0.584, and it's significant. Right? So that's what we see there. Now, a question here is, how do these values compare with the linear regression between GDP per capita and life expectancy? So let's have a look at this. So let's do a linear regression now. Linear regression. And remember, our old results are still here, so we can compare them. compare with a linear regression between GDP per capita and life expectancy. So let's say we're looking at life expectancy is what we're measuring, dependent variable, and we're changing GDP per capita. What I want you to notice is some similarities here. Firstly, you can see the correlation number is the same here. The correlation statistics the same with this big R as well. But we have additional information with the linear regression model. It allows us to tell us what the amount of variance is explained. So the amount of variance in life expectancy explained by GDP per capita is 34.1%, right? It also allows us to interpret the slope that we see here. So we could see that for every 1 unit increase in GDP per capita, there's a 0.001 unit increase in life expectancy. So we get some really valuable information that we don't get with just a simple correlation. But what I want to show here is just that in a linear regression model, you can see that when it's just two variables, the correlation is going to be the same because this big R is what that reflects, right? Excellent. So let's ask a little bit more complex question using the skills we learned just then previously in regards to filtering. In 2007, what's the correlation between GDP per capita and life expectancy? So it's the same analyses we just did, but we just need to apply a filter. So we can go data, filter, and we want to say what the life correlation is for when the year is 2007. Year equal 2007. And we can see these numbers automatically updated, right? So I just need to put active and the years will update, right? If it's inactive, it goes back to what it was previously, 0.584. But if I put it as active, you can see it's graying out everything and it shows only for when the year is 2007. And we can see that the size of the effect actually increases quite a lot. And the variance explained it goes up to 46.1% of variance, whereas previously it was 34.1. So clearly GDP per capita explains much more the variance in life expectancy in 2007 compared to when you just look at all the years combined. Yeah, so that's some really interesting information there. So let's use some descriptive statistics to now see how the mean life expectancy varies by each continent in 2007. Oh, sorry. So to do that, we go to data, analyses, exploration, and just descriptives. And we'll look at life expectancy and the continent, how it varies by continent. And the data set still has the filter applied, so it only selects the 2007 groups. Now we just want to look at the mean life expectancy. So we can remove the median, min, max, standard deviation, try to clean up this table a bit. And it shows us the mean life. I can remove the missingness and yeah, we'll leave that. So here's the mean life expectancies for 2007, how it varies between each of the countries, right? And that's what we see there. So it's the mean for 2007 for Africa, continent, sorry, is 54, Americas 73, Asia 70, Europe 77, Oceania 80. So now what I want you to do is conduct a linear regression between life expectancy as the dependent variable and continent as the independent variable. So we'll go regression, linear regression. We want life expectancy as the dependent variable, and we want continent as the factor. Now what I want you to do is I want you to compare the descriptives to this table, and let me know if there's anything that you see as a similarity. All right, what similarities do you see there? I'm assuming when I'm asking these questions, you're pausing the video, but it's fine if you're not. So what may stick out to you is that the intercept, 54.806, seems a little too suspiciously similar to the mean life expectancy of Africa. Now, what's happening here is continent is a factor, right? It's a grouping variable. So we have 5 continents. We have Americas, Asia, Europe, Oceania, and Africa. And what this regression model is showing us now is it shows us the relationship first between the continent and life expectancy, the amount of variance accounted for, which is 63.5% of the variance. But these estimates, these beta estimates, what do they refer to? Well, they actually refer to the difference in these means, right? So what the predictive model will do, it'll set the baseline arbitrary, based on, I think it's usually alphabetically. So Africa is first in the alphabet, it goes A, then F, so Africa will be the baseline. So the intercept is 54.806. And then America's is 18 years above 54.806. So if we add 18.802 to 54.806, we will get the mean life expectancy of America, which is 73. So what this is showing us is the difference in means between these continents. And similarly, we see the same thing here. So Asia, you see how it says Africa here. So it's Asia has 15.922 years greater than Africa, which is the intercept, which has been set by Jamovi because of alphabetically. So 54 is here. So 54 plus 15.922 gives you 70.728. So these estimates reflect the difference between these groups. And this can be a really powerful tool because it shows you a number of things about not only the difference in the estimates, but with the means for these continents, but allows us to, in a regression model, adjust for other factors. So we can have adjusted means and see what's the outcome as a result of adjusting for other variables. So hopefully this is blowing your mind and you're finding it very useful. And you can see how it may be useful if, say, you want to see what the effect is of some sort of intervention or drug treatment on a group compared to a control group. And you can use a regression model to do so. Now, say you want to, maybe your control group here, you want to see how many more years people have in living in Europe compared to Asia. You want Asia to be the baseline group. To do so, we just need to change the reference level. So we go to reference level and we change the reference level to Asia, and it will set the reference level to Asia. Notice how the amount of variance doesn't change. It's arbitrary what the reference level is. It just is a point at which other estimates are calculated. And now we can see that the difference in these estimates reflect the mean difference compared to Asia. So America is 2.88 years greater mean life expectancy compared to Asia in 2007. Now, this is very powerful. Now, you may ask, why can't we just use these means and descriptives and look at the differences? Well, it's because these are just the raw values. And whilst this shows the raw value, it doesn't account for adjusting for additional predictors, which is really what you'll do in a real world research setting. So you may ask questions such as, how much additional variance in life expectancy does GDP per capita explain over and above continent? So we can put GDP per capita across here into covariates. And we can go into the model builder to do, so this is just a hierarchical regression, which we've done before. And we put how much additional variance in life expectancy does GDP per capita account for. So we'll put that into the new block, add a new block, drag the variable across. And we can see the change in R squared is 7.8%. So the amount of additional variance explained in life expectancy as a result of adding GDP per capita is 7.8%. Now, importantly, you can see that these estimates vary slightly because they're now not only reflecting the difference between groups, but the difference between groups compared to the baseline, which we set to Asia, after adjusting for GDP per capita in Model 2. So that's what we see there. And we can see that the difference between the two models is significant, and we can see that the main significant difference is between Asia and Africa after accounting for GDP per capita. So that's it. That's really public data analysis. Hopefully you enjoyed this tutorial. It was more of a application to show you all the skills that you've learned, applying it to real world questions that can be answered in a real world data set. So you can look at some of the resources I put up online in regards to data sets, and you can have to play around just like we're doing here. See if you can select certain rows out, see if you can conduct analyses, correlations, multiple linear regression or hierarchical regression, and apply some of the concepts that you learned today and in this course. And hopefully it helps as well in your future research careers, or if you're ever doing data analyses for any reason, whether it's even analyzing your own biometrics information, if you want to see how your sleep patterns are going, or if you're exercising better, or any effects in your own life, you can use these tools and learn from there. But as always, if you have any questions, put them on the discussion forums, and there's a few up there for you to ask your questions. Other than that, hopefully you enjoyed this tutorials and go on and forth and conquer with your data analysis skills. Cool. Thanks, guys.